Right now, inside every atom in your body, sits a particle that physics still cannot fully explain. It is called the proton. Scientists have studied it for 100 years. They still argue about how heavy it is, how big it is, and how long it will live. Here is the strangest part. The proton is made of 3 tiny pieces called quarks. Add up those pieces and they give you almost nothing. 99% of your weight comes from something else entirely. Today we go inside, a place with pressure stronger than a neutron star, a spin that seems to come from nowhere, a clock ticking toward the death of matter itself. If this kind of mystery grabs you, take a second to like and subscribe. It helps more than you know. Now take a breath. We are going in. Hold up your hand and look at it. Every part of it, the skin, the bone, the blood, is built from atoms, trillions of them, and packed into the heart of every single atom sits a tiny ball called the proton. You're made of protons. So is this planet. So is the sun, the air, the ocean, and every star you have ever seen. The proton is the most common building block of the solid world around you. It has been sitting inside atoms since a few seconds after the universe began. You would think we understand it by now. We do not. Scientists have poked at the proton for more than 100 years. They have smashed it, frozen it, and blasted it with beams brighter than anything in nature. After all of that, some of the most basic questions about the proton still have no clear answer. How heavy is it really? And where does that weight come from? How wide is it? Does it spin the way we always thought? Will it live forever? Or is it slowly falling apart right now, deep inside you? These sound like simple questions. A 15-year-old could ask them at dinner. The strange thing is that the smartest people alive, using machines that cost billions of dollars, still argue about the answers. Here is one taste of how weird this gets. The proton is made of smaller pieces. When you weigh those pieces on their own and add them up, you get almost nothing, around 1% of the proton's true weight. The other 99% seems to come out of empty space. Picture that for your own body. Step on a scale tomorrow morning. Almost none of that number comes from actual stuff. Most of it is a kind of trapped energy, buzzing inside particles far too small to ever see. The proton is roughly 100,000 times smaller than the atom that holds it. If a single atom were blown up to the size of a football stadium, the proton would be one marble sitting on the center line. Everything else would be empty air. Yet that marble carries almost all the weight and holds the whole thing together. For a long time, people pictured the proton as a solid little dot. Simple, boring, a full stop at the end of a sentence. The real answer turned out to be far stranger. Inside that dot is a storm, a churning, screaming, high-pressure furnace, filled with things that flicker in and out of being. Some of them we can barely describe. A few of them we still cannot explain at all. Over the next chapters, we are going to climb inside this tiny world one step at a time. We will meet the pieces that build the proton. We will find a force that works backwards. We will feel the most crushing pressure ever measured by human beings, hiding in a speck far smaller than a germ. We will end at a question that keeps physicists awake at night. If the proton can die, then one distant day, so can everything you love. Before we crack the proton open, we need to shrink down and see where it lives. So let us take one normal atom, the kind floating in your next breath, and pull it apart. Picture a single atom from the air you just breathed in. It is far too small to see, even with a good microscope. Millions of them could hide behind the width of one human hair. Now imagine you could zoom in until that one atom filled the whole sky. What would you find? Mostly nothing. Empty space. The atom is almost entirely a vast, silent gap. That surprises most people. The stuff you think of as solid, a desk, a wall, your own arm, is mostly emptiness held in shape by tiny forces. Way out at the edges you would see a faint blur. Those are the electrons. They are unbelievably light, and they move so fast that they smear into a cloud. They form the outer shell of the atom. They decide how it links to other atoms and how it feels to the touch. When your hand presses on a table, it is electrons pushing back against electrons. You never actually touch the table. You feel their force stopping you. The heart of the atom lies deeper. Fly past the electrons straight through all that empty space toward the very center. There, packed into a tiny knot, sits the nucleus. The nucleus holds almost all the weight. Even though it is thousands of times smaller than the whole atom, it carries more than 99% of the mass. Remember the football stadium? The nucleus is that marble on the center line. Zoom into the nucleus and it breaks apart into little balls stuck together. Two kinds. One kind carries a positive charge. Those are the protons, our main character. The other kind carries no charge at all. Those are the neutrons, the quiet cousins. What makes an atom oxygen instead of gold or iron? Just one thing, the number of protons. 8 protons, and you have oxygen. One proton by itself is hydrogen, the fuel of the sun. 6 is carbon, the base of every living thing. 79 is gold. Change the proton count and you change the element itself. Old alchemists spent their whole lives dreaming of this and never managed it. So the proton is more than a building block. It is the name tag. It decides what a lump of matter actually is. Now here comes the odd part. Every proton carries a positive charge. In science class you learn that like charges shove each other away. Two positive things should race apart hard and fast. Yet inside the nucleus, protons sit crammed together tighter than sardines in a can, packed closer than should ever be allowed. They should blast apart in an instant. They do not. Something holds them there. Something far stronger than the pushing. That something is a force so powerful it makes ordinary electricity look gentle. We will meet it soon, and it breaks nearly every rule you think you know. The real shock is what a single proton turns out to be made of. For a long time, everyone thought the proton was solid. The smallest thing there was, a tiny brick with nothing inside. Then, in the 1960s, scientists fired beams deep into the proton to check. They wanted to know if anything was hiding in there. Something answered. Something small and hard and hidden was waiting inside. The proton had a secret, and it was about to split wide open. The moment those beams bounced back, everything changed. Scientists were firing high-speed electrons straight at protons like shooting tiny bullets at a wall to learn what it is made of. If the proton were a smooth, solid ball, the bullets would slip through or skim off gently. Instead, some of them slammed into something and ricocheted hard, flying off at wild angles. That could only mean one thing. The proton had structure. It held lumps inside, real and separate. Those pieces got a strange name. Quarks. The word was lifted from a line in a novel, chosen almost as a joke. The things themselves are no joke at all. Quarks are, as far as anyone can tell, truly basic. They sit at the very bottom floor of matter, with nothing smaller hiding inside them. A proton holds 3 main quarks. 2 of one type, called up quarks, 1 of another type called a down quark. 2 up, 1 down. That short recipe builds the particle that builds you. The neutron, that quiet cousin from before, uses almost the same recipe with the parts flipped. 2 down quarks and 1 up, a tiny switch, and yet it changes the neutron's charge and its whole personality. For a moment, the mystery looked solved. A proton is 3 quarks. Case closed. Physicists felt pretty proud of themselves. Then they tried to check the weight, and the neat little picture fell apart. They knew exactly how heavy a proton was. They could measure that with great care, and they were learning how heavy a single quark was. So the plan seemed easy. Take the 3 quarks, add their weights together, and you should land on the weight of the proton. The answer came back almost laughably wrong. The 3 quarks, added up, gave only a thin sliver of the proton's real weight, around 1%. The other 99% was simply gone. Imagine weighing a full school bus. Then you take out every part inside it, the seats, the engine, the wheels, the thick metal frame, and you weigh all of that too. And the total comes out to about the weight of a single backpack. Where did the rest of the bus come from? That is the exact spot physicists found themselves in. Almost all of your weight, and the weight of every mountain and every star, comes from a source that the 3 quarks alone cannot explain. There was a second shock waiting right beside the first. It was about charge. You already know that charge comes in whole units. An electron carries 1 full negative charge. A proton carries 1 full positive charge. Clean, tidy, whole numbers. That is how it works everywhere you look in daily life. The quarks inside the proton refused to follow that rule. Their charges came in pieces, fractions, thirds of a charge which everyone had believed was flat out impossible. So now there were two riddles tangled together: a proton whose weight came mostly from nowhere, and a proton built from pieces whose charges should not even be able to exist. To untangle both, we have to look closer at these quarks. We have to see how truly alien they are. Because once you understand the rules they break, the missing weight starts to make a terrible kind of sense. Try to grab a single quark and pull it out of a proton. You will fail. Everyone always has. Start with the charge riddle because the answer is oddly beautiful. An up quark carries 2/3 of a positive charge. A down quark carries 1/3 of a negative charge. Now add up the proton's recipe. 2 up quarks give you 2/3 plus 2/3, which comes to 4/3 of positive charge. Then the single down quark takes away 1/3. 4/3 minus 1/3 leaves exactly 1. One clean, whole, positive charge. It works like paying for a $1 candy bar using only strange coins worth 2/3 and 1/3 of a dollar. The coins look impossible on their own. Handful by handful, they still add up to a round number at the register. The proton looks perfectly normal from outside, even though its pieces are anything but. Quarks are strange in deeper ways too. Nature has 6 different types of them. Physicists gave them playful names. Up and down are the 2 lightest, and those are the only ones inside an everyday proton. The other 4, called charm, strange, top and bottom, are heavier and rarer. They burst into being for a flash inside giant crash machines, then vanish. The top quark is a true monster. One of them weighs more than a whole atom of gold, even though a quark is a single point with no size at all. Sit with that. A quark takes up no room. It has no width, no surface, nothing to touch. As far as we can measure, it is a pure point in space. Yet a few of these sizeless specks locked together build a proton that does have a size, a weight, and a shape. There is also a hidden kind of charge that quarks carry, stacked on top of the electric one. Scientists nicknamed it color, though it has nothing to do with the colors your eyes see. The name is just a label, because it comes in 3 versions. Mix all 3, and they balance out, the way the 3 colors of light on a screen blend into plain white. Every quark carries one of these 3 color charges. Inside a proton, the 3 quarks each take a different one, and together they cancel into something calm and neutral on the outside. This color charge is the whole key. It is the handle that the strongest force in nature grabs onto. It is the reason quarks cling together with such savage strength, and it is the reason you can never yank one loose. Because that is the truly wild part. We know quarks are real. We have watched them kick back when we fire beams at them. We can measure their charge and their spin, yet in the entire history of science, no one has ever held a lone quark on its own. Not once. Every other piece of matter can be set free. You can rub an electron right off an atom. A static shock on a dry day is loose electrons leaping across a gap. But a quark will not leave home. Pull on it, and it fights back harder the more you pull. That backward behavior is the doorway to everything. It hides the proton's missing weight. It locks the quarks in their cage. To open that door, we first have to solve the mystery of the vanished 99% and follow it straight to its source. So where did almost all of your weight go? Start with the quarks themselves, because their weight is a shock. Each one is astonishingly light. The 3 quarks inside a proton, added together, make up only about 1% of it. If your whole body followed that same rule, then out of everything you weigh, the actual quark stuff would be about the size of a small snack. Now quarks do have that little bit of weight, and even that has a famous source. You may have heard of the Higgs boson. When scientists found it, it made headlines all over the world. Newspapers called it the particle that gives everything its mass. Crowds cheered. It won a Nobel Prize. Here is what almost no one mentioned in those headlines. The Higgs only explains that 1%. It hands the quarks their tiny personal weight, and that is all. It has almost nothing to do with the other 99% of you. Let that flip your view of your own body. The famous mass particle, the one they built the largest machine in history to find, accounts for a sliver of what you weigh. The rest comes from somewhere else entirely, somewhere far stranger and far less talked about. Think of a brick wall. You would guess its weight comes from the bricks. That is common sense. Now imagine you learn that the bricks are almost weightless, and nearly all the wall's heft comes from the invisible force holding the bricks in place. You would stare at that wall and wonder what force could possibly be that strong. That is the real puzzle of the proton. The pieces barely weigh a thing, yet the finished proton is heavy, so the weight comes from whatever binds the pieces together. This bothered physicists deeply because weight was supposed to be simple. Weigh the parts, add them up, done. It works for a car, it works for a sandwich, it works for a planet. Take anything apart, weigh the pieces, and the numbers match. The proton laughed at that idea. Its pieces come out to almost nothing, and the whole thing comes out heavy. The math should not close, and yet the proton sits there, in every atom of you, weighing exactly what it weighs, as if daring us to explain it. The answer, when it finally came, sounded almost impossible. The missing weight is made of energy. Pure, raw, trapped energy, locked inside the proton, behaving as if it were solid matter. That idea traces back to the most famous equation ever written, a short line from Albert Einstein. It says that energy and mass are two faces of the same coin. Energy can act like weight. Weight is really energy in disguise. Most people have seen the equation on a poster or a shirt. Very few realize that it is the reason they weigh anything at all. So the 99% was there all along, hiding in plain sight, wearing a different mask. It is the energy of a battle happening inside the proton every moment, without rest. To understand that energy, we have to watch what the quarks are actually doing in there, because they are moving in a wild way, a way that turns motion itself into weight. The quarks inside a proton are racing. Deep in that tiny space, the three quarks tear around at nearly the speed of light. They never slow down. They never stop. They fly, twist, and slam back and forth, trapped in a box far too small to picture, moving faster than anything you will ever witness with your own eyes. Motion like that carries energy. You already know this in your body. A thrown baseball stings your hand harder the faster it flies. A car crash at highway speed does far more damage than a slow bump in a parking lot. Speed is energy, and energy has power. Now bring back that short, famous equation from Einstein. Energy and weight are the same thing wearing different clothes. So all that furious quark motion, all that speed packed into a tiny space, does something amazing. It turns into weight. The faster the quarks move, the heavier the proton becomes. This is the first big piece of the missing 99%. A large chunk of your weight is simply the energy of quarks sprinting in circles forever inside every proton in your body. You're heavy because, in a sense, you're full of motion. There is a second piece, and it is even stranger. It comes from the force holding the quarks in. Remember the backward force from before, the one that pulls harder the farther you stretch it. Picture it as a spring linking the quarks. When quarks drift apart, that spring stretches and stores energy, the same way a stretched rubber band stores the snap it is about to release. The proton is packed with these springs, all stretched, all loaded, all holding energy at once. And stored energy, by Einstein's rule, is also weight. So now you can see the full picture of what you're made of. A little bit of your weight comes from the quarks themselves, the part the Higgs handed over. The rest, the giant share, comes from two things: the energy of quarks racing near light speed, and the energy locked in the force springs pulling them back. None of that is solid stuff. It is motion and tension, frozen into the form of a particle. When you stand on a scale, most of that number is energy pretending to be matter. Here is a comparison to make it stick. Imagine a swarm of bees inside a sealed glass jar. Weigh the jar while the bees are calm and sleeping. Now shake the jar so every bee is flying at full speed, buzzing and crashing around inside. In the strange world of the proton, that shaking jar would weigh more, just from the frenzy of movement. The proton is that jar, shaken forever, its bees never once landing. This is why the proton fooled everyone for so long. People kept trying to find the weight in the parts. The weight was never really in the parts. It was in the storm between them. But storms need a source. Something has to keep the quarks racing. Something has to keep those force springs stretched and loaded, holding all that energy in place second after second, for billions of years without ever running down. That something is a swarm of particles we have not truly met yet. They carry no weight of their own, and somehow they supply nearly all of yours. It is time to meet the glue. The thing that supplies almost all your weight has no weight of its own. Meet the gluon. The name is a clue. Gluons are the glue of the proton. They are the particles that carry the strong force, the messengers that pass between quarks and hold them together. Every time one quark tugs on another, a gluon flies between them to deliver the pull. Photons of light carry the force that lights your room. Gluons carry the force that builds your body, and they are everywhere inside the proton. Countless gluons fill the space between the quarks, a whole blizzard of them, flashing back and forth so fast that the inside of a proton is more gluon than anything else. Here is the part that breaks people's brains. A gluon has zero mass. On its own it weighs nothing at all, just like a particle of light. Yet the energy carried by this swarm of weightless messengers becomes most of the proton's weight. Most of your weight. The heaviest thing about you is built from a storm of things that weigh nothing. Picture a crowd at a packed concert. No single person is the concert. Yet the roar, the heat, the surge of the crowd is real and powerful, and it comes from all of them moving together. The gluons are like that roar. Each one is nothing. Together, they are almost everything. So let us finally add up the missing 99% now that all the players are on the field. A tiny slice of the proton's weight comes from the quarks, the part the Higgs gave. A big share comes from the quarks racing near light speed. Another big share comes from the gluons and the force energy stored between everything. Stack those energies together, and you get the full weight of the proton right on the money. The riddle is solved, and the answer is almost poetic. You're mostly made of force. You're mostly made of energy and motion. The solid feeling of your own hand is a trick played by a swarm of weightless glue moving faster than thought. This also cracks open a bigger truth about the universe. Nearly all the ordinary weight in existence, every planet, every star, every galaxy you can name, gets its heft this same way. The visible universe is heavy mostly because of the strong force churning inside protons and neutrons. Take away that churning, and the cosmos would weigh almost nothing. Scientists can even check this now. They build models of a single proton inside giant supercomputers, tracking the quarks and the blizzard of gluons. When they add up all the energy, the weight they calculate matches the weight we measure in real experiments. The strange story holds. The glue really does carry the load. So the proton makes a kind of sense at last. 3 quarks, a swarm of gluons, a furious amount of energy, all adding up to the weight you carry every day. One thing still refuses to sit quietly though. That backward force, the one that grabs quarks and never lets them go, the one that gets stronger the harder you pull, when every other force in the universe does the opposite. A force that behaves that way should not even be possible, yet it is the most powerful force there is, and understanding it means throwing out almost everything your gut tells you about how the world works. Every force you have ever felt gets weaker with distance. The strong force does the exact opposite. Think about the forces in your daily life. A magnet grabs a paperclip when you hold it close, and the pull fades away as you lift it back. Gravity keeps you stuck to the ground, yet it loosens its grip the farther you drift from Earth. Move away from any normal force, and it eases off. That rule feels so obvious that you never question it. Closer means stronger, farther means weaker. The force inside the proton flips that on its head. When 2 quarks sit close together, the force between them is gentle, almost nothing. The quarks drift around loosely, barely feeling any pull at all. But try to move them apart and the force wakes up. It grows. The farther you drag one quark from another, the harder the force yanks them back. There is only one everyday thing that behaves like this, and you have held it in your hand. A rubber band. When it hangs loose, you feel no tension. Stretch it a little, and it starts to pull. Stretch it far, and it fights you, straining to snap your fingers back together. The strong force is a rubber band wired into the deepest level of matter, joining every quark to its neighbours. This one strange rule explains the whole prison. It is why no quark can ever escape a proton. To pull a quark out, you would need to stretch its band all the way to freedom. But the farther you pull, the harder the band resists, so the escape only gets more impossible the closer you get to success. The quark is trapped by a force that grows meaner with every inch. It also explains the crushing energy we found earlier. Stretch a rubber band and it stores energy, ready to fire back. The proton is packed with these bands and the force keeps them loaded. That stored energy is a huge part of the weight you carry. Weight once again hiding inside tension. Now think about how backward this is compared to everything else. Pull two magnets apart and at some point they simply let go and you walk away holding both. Try that with quarks and the force never quits. It just keeps climbing, stronger and stronger, refusing to release, as if the universe itself is holding the proton shut. This is why physicists call it the strong force, and the name is almost too plain. At the tiny scale of the proton, it is the most powerful force in all of nature. It crushes the pushing of electric charge, the same pushing that should blow protons apart. It beats gravity so badly that gravity looks like a rumour by comparison. Inside the nucleus, this force is the boss, and nothing else comes close. Yet a rubber band, if you keep stretching it, does one more thing. It reaches a breaking point. It snaps. So here is the question that hangs over everything. What happens if you actually manage to stretch the bond between two quarks far enough to break it? Do you finally get your lone quark, free at last after all this trying? The answer is one of the wildest tricks in the universe. When that bond snaps, freedom slips away again. Something new is born out of pure nothing, and the proton keeps its prisoners after all. Snap the bond between two quarks, and the universe does something you would never guess. It refuses to let you win. Here is the setup. You have two quarks joined by that rubber band force. You start pulling them apart, feeding in more and more energy, stretching the band tighter and tighter. You can feel the finish line. One more pull and the band should break, leaving you holding a single lonely quark. The first one ever caught alone. The band does break, but at the very instant it snaps, something appears where the break happened. Two somethings, actually. A brand new quark and a new anti-quark, its mirror partner. They pop into existence out of the raw energy you poured into the stretch. Remember Einstein's rule. Energy can turn into matter. You spent all that effort stretching the band, and that effort was energy, and the snapping band cashed that energy in to build fresh particles. So each loose end grabs a new partner instantly. Instead of one free quark, you now have new pairs, each one bound up again, each one still trapped. It is like cutting a magnet in half, hoping to get a single north pole all by itself. The moment you cut, two fresh poles appear at the cut, and each piece is a complete little magnet again, north and south. You can chop forever and never hold a lone pole. The quarks play the same cruel trick. Cut the bond and new quarks bloom to keep every piece paired. This is why no one has ever seen a lone quark and why no one ever will. Nature has a rule buried deep in the strong force. Quarks come locked in groups, and they stay locked in groups. Physicists call it confinement, a fancy word for a simple, stubborn fact. You're allowed to look inside the proton. You're never allowed to take a piece out. You might think this is just an idea on a chalkboard, impossible to test. It is not. Scientists watch it happen. When they smash particles together at tremendous speed in giant machines, quarks do get flung outward with enormous energy, and every single time as those quarks fly apart, the bonds snap and new particles bloom along the way. What comes out is a spray, a narrow shower of particles all travelling together. Physicists call these sprays jets. They see them constantly. A jet is the fingerprint of a quark that tried to escape and could not, dressed instantly in a crowd of new partners. So the proton keeps its secrets by cheating. Pull a piece loose and it simply makes more pieces, faster than you can grab anything. The harder you try to open the cage, the more prisoners appear inside it. By now the proton looks like a fortress. Quarks locked in by a backward force, a band that grows stronger with distance and heals itself the moment it breaks. It feels like the most sealed, most guarded object in nature, which makes the next fact almost impossible to believe. Deep in the very centre of the proton, where the quarks crowd closest together, that mighty force nearly disappears. Right at the core, the quarks are almost free, roaming as if no cage existed at all. The strongest force in the universe has a hidden weakness, and finding it earned a Nobel Prize. At the very centre of the proton, the strongest force in nature almost switches off. This makes no sense at first. We just watch the strong force trap quarks snap back when stretched and build new particles rather than let one escape. It sounds like a force with no soft side at all, yet the closer two quarks drift toward each other, the weaker the pull between them becomes. Squeeze them right up against each other and the force fades toward nothing. In that tiny core, quarks float around nearly free, barely feeling the cage that holds them. So the strong force has two faces. Far apart, it is a monster that never lets go. Up close, it is a whisper. The rubber band from before shows it perfectly. Hold both ends together in your palm and the band goes limp and weightless. Pull them apart and it strains and fights. The force lives entirely in the distance, and at zero distance it nearly vanishes. When physicists first worked this out, they could hardly believe their own math. Every force they knew did the opposite. Bring two magnets together and the pull grows stronger, right up until they clack shut. Fall toward a planet and gravity climbs the whole way down. Closeness was supposed to mean strength. The strong force broke that rule so cleanly that many scientists assumed there was a mistake in the numbers somewhere. 3 young physicists chased the idea down anyway, back in the early 1970s. They pushed through the math and showed it was real. The strong force truly does fade to almost nothing when quarks get close enough. They gave the effect a name that sounds like a riddle. They called it freedom at short range. Quarks that are jammed together are strangely the most free. That discovery cracked open the whole science of the proton, because it meant scientists finally had a way to calculate what happens inside. When the force is weak, the math becomes possible to solve. Decades later, in 2004, those 3 physicists were handed the Nobel Prize for it. They had found the secret setting that lets the strong force build a stable proton at all. Think about what this does to the picture in your head. The proton is really 2 places at once. Its edge is a prison wall, a fierce boundary that no quark can cross. Its core is an open field, where quarks wander loose and easy. The same 3 quarks feel a savage grip near the surface and near total freedom at the centre. One particle, 2 completely different worlds, folded into a speck smaller than anything you can imagine. This double life is exactly why the proton holds together and lasts. The freedom at the core keeps the quarks from crushing into a single frozen lump. The fierce grip at the edge keeps them from ever flying away. Balanced between the two, the proton stays whole. Calm on the outside, wild within. We now have a proton with racing quarks, a blizzard of gluons, a backward force, and a core where the rules relax. It sounds like a full accounting. It sounds like the whole story of what is inside. It is not. The proton holds far more than 3 quarks and their glue. If you could freeze it and count everything crowding that tiny space, you would find a churning, shifting mob that never holds still long enough to count. If you tried to count the pieces inside a proton, you would never get the same number twice. Up to now, the story has been about 3 quarks. 2 up, 1 down, held by gluons. That is the simple version, the one that fits on a poster. It is true, in a way. Those 3 quarks give the proton its identity, its charge, and its name. Physicists call them the real permanent members of the club. The trouble is that the club is never quiet, and it is never empty. Around those 3 quarks churns a wild, shifting crowd of extra particles. More quarks, more antiquarks, more gluons, flashing in and out. The inside of a proton churns like a boiling pot of water, roaring and bubbling, never still for even a moment. Scientists have a name for this seething crowd. They call it the sea, and the sea is huge. At any instant, the proton might hold far more than 3 quarks. It might hold dozens of particles, then a different set a heartbeat later, then another. The 3 permanent quarks ride this storm like 3 swimmers bobbing in a churning ocean, always there, but surrounded by chaos on every side. This changes how you should picture the whole thing. A proton is a riot, a crowd, a blur of activity so fast and so crowded that even the sharpest experiments can only catch smeared snapshots of it. Picture a mosh pit at a concert. From far away it looks like one solid blob of people. Step inside and it is pure motion, bodies slamming, arms flying, people appearing and vanishing in the crush, impossible to count. Now shrink that mosh pit down smaller than a germ and speed it up beyond anything your eyes could follow. That is closer to the truth of what sits inside every atom of you. Here is the fact that should stop you cold. All of this churning, this whole boiling sea fits inside a space 100,000 times smaller than a single atom. And a single atom is already far too small to see. The proton takes the tiniest scrap of space in the universe and packs it with more frantic activity than a stadium full of people. This roaring sea is a real part of why the proton weighs what it weighs. All those extra particles carry energy. All that motion adds to the total. The weight you carry every day comes from more than 3 neat quarks. It comes from an entire hidden crowd that never rests. And that raises a question that sounds impossible. If the proton only truly owns 3 quarks, then where does the rest of the crowd come from? Who invited them? The sea holds far more particles than the proton started with. Something is creating them, filling that tiny space with company that was never there to begin with. The answer is one of the strangest truths in all of physics. Those extra particles are born from nothing, right there inside the proton, over and over, endlessly. Empty space itself is coughing them up. To understand how a particle can appear out of pure emptiness, we have to look at what nothing really is. Because nothing, it turns out, is the busiest place of all. Empty space is alive. It always was. You probably imagine emptiness as a perfect blank. Nothing there. No stuff. No motion. Just a quiet void waiting for something to fill it. That picture feels obvious. It is also wrong, and the proton proves it. Down at the smallest scale of reality, empty space fizzes. It bubbles. It crackles with tiny bursts of activity that flash into being and vanish almost instantly. Particles pop out of nowhere, exist for the shortest sliver of time imaginable, then disappear again before anything can catch them. Scientists call these flickers virtual particles. They are the reason the void is never truly still. How can something come from nothing? The answer hides in a rule of the tiny world, a rule that has been tested countless times. Nature allows energy to be borrowed, as long as it is paid back fast. The universe runs a kind of lightning-quick loan service. Empty space can borrow enough energy to create a particle, but the loan comes due almost at once, and the particle must vanish to pay it back. The smaller the loan, the longer you may keep it. Big loans get called in almost instantly. Inside the proton, this borrowing goes wild. The space in there is packed with so much force and energy that particles wink into being constantly. A quark and an antiquark appear together, dance for the briefest moment, then meet and disappear. A gluon flashes out and dissolves, over and over, trillions upon trillions of times faster than any clock could ever tick. That is the boiling sea from before. It is empty space, borrowing and repaying, filling the proton with a crowd that is always being born and always dying. Picture the surface of a pot just before it boils. Tiny bubbles form on the bottom, rise a little, then pop and are gone, while new ones take their place, endlessly. No bubble lasts. Yet the surface never stops churning. The inside of a proton is that boiling surface, sped up beyond imagination and crammed into a space smaller than a speck of dust. This is one of the deepest ideas in all of science, and it sounds like magic, but experiments confirm it again and again. The flickering particles leave real fingerprints. They nudge the way atoms behave in ways scientists can measure with stunning care. When they run the numbers, the flickers match the measurements almost perfectly. The void really is alive, so the proton is even wilder than a boiling sea of quarks and gluons. It is a place where the emptiness itself keeps giving birth. The 3 permanent quarks are just the steady tenants. Around them, a whole ghost population blinks in and out of reality forever, borrowed from nothing, returned to nothing, never resting. Step back and look at what you're made of now. Racing quarks, a blizzard of weightless glue, a boiling sea, and a void that will not sit still. All of it packed into a particle so small it makes a grain of sand look like a galaxy. With all this chaos, you would expect the proton to be a mess with no simple traits at all. Yet the proton has one habit that looks perfectly clean and steady from the outside. It spins. Every proton turns like a tiny top by a fixed, exact amount, the same for all of them, everywhere in the universe. You would think something that's simple would be easy to explain. It became one of the biggest shocks in the history of physics. The proton spins, and figuring out why nearly broke the people who tried. From the outside, spin is the one clean, simple thing about the proton. Every proton turns like a tiny top. Not sometimes, always. And every proton spins by the exact same amount as every other proton in existence, a fixed measure that never changes. In a world of boiling seas and flickering ghosts, here at last was something steady. Something you could count on. Spin matters more than it sounds. It is a basic trait of a particle, as real as its charge or its weight. Spin is the reason magnets work. It is the reason the machine at a hospital can take a picture of the inside of your body without cutting you open. That whole machine listens to the spin of protons in your cells, so spin runs through the world you live in. It shapes everyday life. For a long while, the answer seemed easy. The proton has 3 quarks inside, and each quark spins on its own. So just add up the 3 little spins, and you should get the spin of the whole proton. Line up the arrows, sum them, done. Physicists were sure of it. It was almost too obvious to check. But science checks anyway. In the 1980s, a team ran a careful experiment to measure exactly how much of the proton's spin came from its quarks. They expected the quarks to supply all of it, or very close. They aimed their beams, gathered their data, and did the math. The quarks supplied almost none of it. The first numbers were staggering. The 3 quarks seemed to account for only a tiny fraction of the spin. Some readings hinted the quarks might explain almost nothing at all. The thing everyone was certain about, the simple sum of 3 arrows, was flat wrong. The proton was spinning, clearly and steadily, and its main pieces were barely responsible. Word spread fast and it landed like a slap. Physicists gave the shock a dramatic name. They called it the proton spin crisis. Careful measurements over the years since have softened the blow a little. The best count today says the quarks carry only about 1/3 of the spin, better than almost nothing, but still far from the full amount everyone had promised. So a giant piece of the spin was simply unaccounted for, missing. The proton turns by a fixed, exact amount, and when you tally up the spin of its 3 quarks, most of the total is nowhere to be found. It felt like watching a spinning top and discovering that the top itself was barely moving, while some hidden thing kept it turning. Sit with how strange that is. This is the most common particle in the solid universe. It sits in every atom of your body, spinning right now, trillions upon trillions of times over. And for decades, the smartest people alive could not say where most of that spin came from. A basic question about a basic particle, and the honest answer was a shrug. The crisis sent physicists digging back into the proton, hunting for the missing turn. If the 3 quarks only give about 1/3, then 2/3 is hiding somewhere inside that boiling chaos. Something else in there has to be spinning too, or moving in a way that adds up to a turn. There were 2 suspects, and chasing them down would take more than 30 years. 2/3 of the proton's spin was missing, so physicists went hunting for it. They started with the most obvious suspect, the gluons. Remember, the proton is stuffed with them, a whole blizzard of the weightless glue that carries the strong force. And gluons, it turns out, can spin too, just like the quarks. So maybe the missing turn was hiding there. Maybe the gluons were quietly spinning and adding their share to the total. It was a good idea, and scientists chased it hard. They built experiments to measure how much the gluons spin inside the proton. The work was brutally difficult. Gluons are slippery, flashing in and out, impossible to pin down cleanly, but slowly the measurements came in, and gluons do help. Their spin adds a real piece to the total, filling in part of the gap the quarks left behind. Even with the gluon spin added, though, the book still did not fully balance. Quarks giving about 1/3, gluons giving some more, and still the numbers came up short. There had to be one more source of spin hiding somewhere in that tiny storm. The second suspect brought in a whole new idea. Motion. Orbiting motion. Think about how the Earth moves. It spins on its own, turning once a day. But it also travels in a great loop around the Sun. 2 different kinds of motion at once, its own spin and its wider orbit. Particles can do the same. A quark inside the proton does more than spin on its axis. It also swirls around inside that little space, circling, looping, riding the boiling sea. And that circling motion carries its own kind of turn, which adds to the grand total. So the full picture of the proton spin came together like a recipe with several parts. 1/3 or so from the quark spinning, a share from the gluons spinning, and the rest from the swirling, orbiting motion of the quarks and gluons as they race around inside. Add all of it together, and at last you can build the steady, exact spin we measure from outside. That sounds tidy on paper. In practice, it has been one of the hardest measurements in all of physics, counting orbiting motion inside a boiling storm of ghost particles in a space 100,000 times smaller than an atom, is close to a nightmare. Scientists have chased these pieces for more than 30 years in labs across the world, and they are still tightening the numbers today. Here is the honest state of things. Physicists now understand roughly where the spin comes from. Quarks, gluons, and orbiting motion sharing the load, but they still cannot add it all up with full confidence and land exactly on the answer. Some of the pieces are still fuzzy. The complete airtight accounting of a single spinning proton does not yet exist. A basic trait of the most common particle in matter, and the final math is still open. That is what makes this story so alive. It stays a live mystery, one that scientists are actively wrestling with right now this year, with new machines and sharper tools, and right now happens to be a remarkable moment. Because just recently, a fresh clue surfaced. Something inside the proton was caught doing a thing no experiment had ever managed to see before. Just this year, scientists caught the inside of the proton doing something no one had ever seen. To feel why it matters, remember where the spin hunt left off. Quarks give about a third, gluons give a share, orbiting motion gives more. The pieces are known, roughly, but the full sum stays fuzzy, and one part in particular has always been a ghost. Scientists suspected that the quarks and gluons do more than add their spins up side by side like coins in a jar. They suspected the pieces overlap and blend, mixing together in a way that affects the total. That blending had a name in the theory. It had never once been measured in the real world. Blending like this has a special flavour in the tiny world. Down at that scale, particles behave like waves, like ripples spreading on a pond rather than like solid balls. And when two sets of ripples cross, they do something water does too. They interfere. Where two crests meet, they pile into a taller peak. Where a crest meets a dip, they cancel into flatness. The pattern that appears comes from the overlap itself, from the way the ripples share the same space. The idea was that quarks and gluons inside the proton interfere like this, their waves overlapping, and that this overlap carries a hidden slice of the answer to the spin puzzle. A slice buried so deep that no machine had ever pulled it into the light. This year, that changed. Scientists reported that they had finally measured this interference inside the proton for the very first time. They caught the quarks and gluons in the act of overlapping, blending their waves, behaving as one connected system instead of separate parts. A thing that had lived only in equations for decades stepped out and became a real measurement. This is a big deal, and here is why. For a long time, people pictured the proton's insides as a bag of separate items. So many quarks, so many gluons, each doing its own job, all added up at the end. This new result shows that the pieces are woven together far more tightly than that. They share, they overlap, they move as a single tangled whole. The proton behaves like a single humming instrument, where every string affects every other. Notice the date on this. This discovery is brand new. It landed in the middle of the year you're living in right now. While you go to school, scroll your phone, and sleep in your bed, there are people in labs pulling brand new secrets out of a particle that sits inside every atom of you. The proton is still surprising us. The book is nowhere near finished. That is the real thrill of this whole story. The proton is the oldest, most common building block in the solid universe, and we're still learning what it is in real time, with fresh headlines every year. So we have wrestled with the proton's weight and its spin, and both fought us hard. You would hope at least one thing about it would be simple. Surely we know how big it is. Surely after all this we can agree on the plane size of the thing. We cannot. Two of the most careful measurements ever made looked at the proton, asked one simple question, how wide are you? And came back with two different answers. Two teams measured the width of the proton with incredible care. They got two different answers, and neither side would back down. This one stings in a special way, because size feels like it should be the easy part. You want to know how big something is, so you measure it. A ruler for a desk, a tape measure for a room. Even for something tiny, you just need a careful enough tool. The proton has a width. It should have one clear number. How hard could it be? Very hard, because you cannot lay a ruler across a proton. It is 100,000 times smaller than an atom, and an atom is already far too small to see. To measure a proton, scientists have to be clever. They study how the proton pushes and pulls on things around it, and from that behaviour they work backward to its size. It is like figuring out the size of a hidden rock in a pond by watching the ripples spread from where it sits. For years, scientists used two trusted methods to find the proton's width, and the methods agreed. Everyone settled on a number and moved on. The size of the proton was considered a solved, boring fact, printed in textbooks, nothing left to argue about. Then a new team tried a sharper method, and their answer came back smaller. The proton, they said, was a touch tinier than everyone had believed. The gap between the old size and the new size was small, only about 4%. For a fence or a football field, 4% is nothing, a rounding error no one would notice. For a number this precise, 4% was an earthquake. These measurements are so exact that they should agree far, far closer than that. A 4% gap between two careful results is a scream. It means one of two things. Either someone made a mistake so subtle that the finest minds could not spot it, or the proton was hiding a secret that the rules of physics did not account for. That second possibility is what set nerves on edge. The whole point of the tools scientists use is that they are trusted completely. If two rock-solid methods look at the same proton and disagree, then maybe the tools are missing something. Maybe there is a crack in our understanding of how the tiny world works, a crack the proton was quietly pointing at. Physicists gave the mess a name. The proton radius puzzle. It sounds small and technical. It shook people because it hinted that our deepest, most tested theory of particles might have a hole in it. A gap in the width of a proton could mean a gap in the laws themselves. So a strange thing happened in the science world. One of the most common particles in existence, the thing inside every atom, suddenly had no agreed size. Ask how wide a proton is, and the honest answer became a fight. Two numbers, both defended by brilliant people, both backed by careful work, refusing to match. Something had to break the tie. And the way scientists finally forced an answer is one of the cleverest tricks in modern physics. They reached into an ordinary atom, plucked out a piece of it, and swapped in a heavier stand-in, a strange cousin of the electron, to feel the proton's size in a way no normal atom ever could. To settle the fight over the proton's size, scientists swapped a piece of the atom for a heavier ghost. Here is the clever idea. In a normal atom, the proton is orbited by an electron. That light. Fast blur out at the edges. The electron feels the proton's size a little, because it sometimes passes very close to it. By studying the electron with great care, scientists can work backward to the proton's width. That is one of the trusted old methods. But the electron is so light and so far out that its reading is gentle, easy to smear, hard to sharpen. So scientists reached for a trick. Nature has a heavier cousin of the electron called the muon. A muon is almost exactly like an electron in every way, with the same charge and the same behavior, except it is about 200 times heavier. And here is the magic. A heavier partner orbits much, much closer to the proton. It hugs the proton tightly, dipping deep into its space, feeling its size far more strongly than a light electron ever could. So they built a special kind of atom. They took the proton, and instead of an electron they placed a muon in orbit around it. This strange heavy atom does not last long, only a flicker before the muon decays away. But that flicker is enough. In that brief moment, the muon presses in close to the proton and reports back its size with a sharpness no ordinary atom can match. It is like the difference between measuring a rock by watching a leaf float past it far away, or by wrapping your hand directly around it. The muon wraps its hand around the proton. Its reading should be the clearest, tightest measurement of the proton's width ever made. In the year 2010, a team led by a physicist named Randolph Pohl finished this experiment and read out their answer. The room must have gone quiet, because the muon reported the smaller size, the tiny proton, the one that disagreed with the old textbooks. That single result turned the puzzle into a full-blown alarm. The sharpest tool ever built for the job had spoken, and it sided against the long-trusted number. For a while, it looked like the proton might truly be pointing at a crack in the laws of physics, a hint that something in our deepest theory was incomplete. Scientists around the world dropped what they were doing and piled onto the problem. In the years since, the fog has slowly started to clear. Newer and better experiments have mostly leaned toward the smaller size, the one the muon found. The scary idea of a broken law has faded a bit. It now looks like the older measurements may simply have been thrown off in ways that were fiendishly hard to spot. Still, even now, not everyone agrees the case is fully closed. The proton guarded its own width so stubbornly that the argument echoes to this day. So think about where we stand. We have chased the proton's weight and found it made of trapped energy. We have chased its spin and found most of it hiding. We have chased its size and nearly cracked the laws of physics doing it. And we have not yet touched the most violent secret of all. Because the muon hugging that proton was pressing against something no human has ever felt. A pressure so brutal it dwarfs the crushed heart of a dying star. Deep inside the proton, the quarks are trapped under a pressure that no human has ever come close to feeling. Pressure is a word you already know. It is the squeeze of water on your ears at the bottom of a swimming pool. It is the crush you would feel diving deep into the ocean, where the weight of all that water presses in from every side. Go deep enough in the sea and the pressure can flatten a submarine like a soda can. That is the raw power of a squeeze. For most of history, scientists only talked about pressure for big things: oceans, planets, stars. The idea of measuring the pressure inside a single tiny particle sounded like a joke. How could something smaller than an atom even have a pressure? And even if it did, how could anyone ever hope to measure it? Then, in the year 2018, a team of scientists did exactly that. For the first time in history, they measured the pressure inside a proton. It was the first time anyone had ever measured this kind of force inside any particle at all. And the answer they found was staggering. Think about what is happening in there. The quarks are locked in by the strong force, that backward rubber band from before. The gluons flood the space, pulling and pushing without rest. All of that squeezing and straining adds up to a real, physical pressure, crushing inward and blasting outward inside a speck far too small to see. The scientists uncovered something beautiful about how it works. At the very center of the proton, there is a fierce outward push. The core is trying to explode, shoving everything away from the middle with tremendous force. If that were the whole story, the proton would blow itself apart in an instant. Near the outer edge, though, the pressure flips. Out there, a powerful inward squeeze takes over, pressing everything back toward the center, holding the proton together. The proton lives in a perfect balance, a screaming outward push at its heart wrapped in a crushing inward hug at its skin. The two forces lock against each other, and the proton holds its shape. Picture a tug of war but wrapped into a ball. The center pulls one way with all its might. The edge pulls the other way just as hard. Neither side wins. The rope stays perfectly still, humming with tension. That frozen standoff is the proton, and it has been holding that exact pose inside every atom of you since long before the Earth was born. This balance is anything but gentle. The forces involved are some of the most extreme in all of nature, packed into the smallest space imaginable. When the scientists finally put a number on the pressure at the proton's core, it broke every record we had. It beat the pressure at the bottom of the deepest ocean. It beat the pressure inside the Earth. It even beat the pressure inside the Sun. In fact, it beat something far more crushing than any of those. There is an object in space so dense that a single spoonful of it would weigh as much as a mountain. Its heart is the most crushed place most people have ever heard of. And the pressure inside a plain proton sitting in your fingertip right now leaves even that monster in the dust. To believe that, you first need to meet the monster. The monster is called a neutron star, and it is one of the most extreme objects in the entire universe. Here is how one is born. A giant star, far bigger than our sun, runs out of fuel and can no longer hold itself up. Gravity wins. The star collapses in on itself in a fraction of a second, then blasts its outer layers away in a titanic explosion, one of the brightest events in all of space. What gets left behind is the crushed core, squeezed past the point of belief. That core becomes a neutron star. Imagine taking the entire sun, a ball more than 800,000 miles across, and crushing it down until it is only about the size of a city, roughly a dozen miles wide. All that mass, squeezed into something you could drive across in a few minutes. The result is almost too dense to picture. Here is the number that makes people gasp. A single spoonful of neutron star would weigh about as much as a mountain. One spoonful. If you could somehow scoop it up and set it on a table, It would punch straight through the table, through the floor, through the Earth itself, dragged down by its own insane weight. Nothing on our planet is packed that tightly. At the very heart of a neutron star, the pressure climbs beyond anything in normal experience. It is the most crushing place scientists know of in the natural universe. For a long time, everyone believed nothing could beat it. Now bring back the proton. When scientists measured the pressure at the center of a single proton, they held it up against the heart of a neutron star, and the proton won. The pressure inside the proton came out about 10 times greater than the pressure inside the most crushing object in the sky. Let that reshape your whole picture of matter. A neutron star is made by crushing an entire sun. It takes the violent death of a giant star to build even one, and yet a plain proton, one of trillions inside a single grain of sand, carries a pressure at its center 10 times fiercer than that. The actual number is almost impossible to say out loud. The pressure at the center of a proton is about 100 decillion. That is one followed by 35 zeros, a number so huge it has no meaning in daily life. You will never count that high. Nothing you touch will ever come close, and this is the part that should stop you cold. That pressure is not far away in space. It is not locked inside some distant dying star. It is inside you, right now. Every proton in your body, in your bones, in your beating heart, holds this same monstrous pressure at its heart. You're made of trillions upon trillions of these tiny pressure cookers, each one out crushing a neutron star, all of them quietly holding you together. You cannot feel it, because the forces sit in perfect balance, sealed inside particles far too small to sense. But it is there, in every cell, every second of your life. So a fair question rises up. If nobody can shrink down and dive into a proton, and no tool could ever survive that pressure, then how on earth did scientists measure it? How do you weigh a force locked inside a thing you can never touch, open, or reach? The answer is one of the cleverest tricks in all of science. To feel the pressure inside a proton, you would normally need gravity. Scientists found a way to fake it. Here is the strange problem they faced. The pressure inside a proton comes from the way its insides push and pull on the fabric of space itself. In the deepest theories of physics, the one tool that feels that kind of push is gravity. So to truly map the forces inside a proton, you would want to poke it with gravity and watch how it answers. But gravity is hopeless for this job. It is by far the weakest force in nature. You only notice gravity at all because the entire Earth is pulling on you at once. For a single tiny proton, gravity is so faint it may as well not exist. Trying to study a proton with gravity is like trying to weigh a feather using the pull of a distant cloud. It will never work. So scientists needed a stand-in, something they could actually control that would press on the proton the same way gravity would and reveal the same hidden forces. It took years of clever thinking to find one. The trick they landed on uses electrons and light. They fire a beam of high-speed electrons straight at the proton. Every so often, an electron dives in close and trades a tiny flash of energy with a quark inside. The quark, jolted by the visit, spits out a burst of light, a real flash, which flies out and gets caught by the detectors. By studying exactly how that light comes flying out, over and over, scientists can work backward to the forces the quark was feeling deep inside. And here is the beautiful part. The math of this light trick turns out to match the math of gravity almost perfectly. So the electrons, with no real gravity involved at all, end up feeling the proton the way a burst of gravity would. They fake the one force too weak to use, and it works. Picture trying to learn the shape of a hidden object in a pitch-dark room by throwing thousands of tiny rubber balls at it and listening to how each one bounces back. One ball tells you almost nothing, but throw enough of them and track every bounce, and slowly the shape of the hidden thing takes form in your mind. The electrons are those rubber balls, and the proton is the object in the dark. This was slow and it was hard. To pull one clean answer out of the chaos, the team needed a mountain of these collisions. They gathered around 500,000 of them. Then they spent close to 10 years, an entire decade, carefully untangling the data before they trusted the result. When it was finally done, they had achieved something no one had ever managed before. They had measured a real, physical, mechanical force inside a particle smaller than an atom, using nothing but electrons and light as a fake form of gravity. The record-breaking pressure at the proton's core came straight out of that work. It stands as one of the most creative measurements in the history of science, a way to touch the untouchable, a way to feel a force buried inside a thing you can never crack open. And yet, for all that cleverness, the proton still guards a question far heavier than its pressure. A question that reaches past your fingertip and out to the fate of the whole universe. Will the proton live forever? Here is a question that sounds simple and turns out to be one of the deepest in all of science. Does the proton ever die? Think about what you have learned so far. Every atom in you holds at least one proton. Every rock, every ocean, every star is built on them. The proton is the great survivor, the steady foundation under all solid matter. It has been sitting inside atoms for almost the entire life of the universe, close to 14 billion years without ever falling apart. So most people would guess the proton is eternal, forever stable, a thing that simply never breaks. For a long time, scientists guessed the very same. They treated the proton as a permanent brick, the one piece of matter you could always count on. Then a troubling thought crept in. Almost everything in nature, if you wait long enough, eventually changes or decays. Heavy, unstable atoms break down over time. Even the light from stars fades as they burn out and die. The universe is full of things that seemed solid, and then, given enough time, came undone. Why should the proton be the one exception? Why should it, alone, last forever? Some of the boldest ideas in physics say it should not. They predict that the proton, the rock under everything, is very slowly falling apart. That deep inside you, right now, there is a faint, almost impossible chance that a single proton could suddenly break, flash into other particles, and vanish. Sit with what that would mean. If protons can die, then nothing is truly permanent. Not you, not the Earth, not the stars. Everything you have ever seen would be living on borrowed time, slowly crumbling toward an end, one lost proton at a time. The whole future of the universe hangs on this single question. There is only one way to know for sure. You have to catch a proton in the act of dying. You have to actually see one break. And this is where it gets maddening. If protons do decay, they do it so rarely that you could watch a single proton for the entire age of the universe, over and over, and almost certainly never see it happen. The odds of catching one are beyond tiny. It would be like staring at one specific grain of sand on one specific beach, waiting for it to crumble to dust, when that grain might outlast every star in the sky. So how do you ever catch something that rare? You cheat with numbers. You do not watch one proton. You gather a staggering, unthinkable pile of protons all in one place, and you watch every one of them at once. If each proton carries a tiny chance of dying, then with enough of them crammed together, maybe, just maybe, one will break while you happen to be looking. That single idea launched one of the strangest hunts in history. Scientists went searching for a way to gather an ocean of protons and stare at them, without blinking, for years on end, hoping to witness a single silent death. Before we see how they did it, we have to understand why anyone believes the proton can die at all. The reason reaches all the way back to the first moments of the universe, and a dream about how everything might once have been one. To understand why the proton might die, we have to travel back to the very beginning of everything. Today the universe runs on a handful of basic forces. There is the strong force, the one holding quarks inside the proton. There is the force behind electricity and magnetism, which lights your home and runs your phone. And there is a third, quieter force, called the weak force, which controls certain kinds of radioactive change. These forces feel completely different from one another. They have different strengths and different jobs. Yet many scientists believe that, long ago, they were all the same thing. In the first tiny sliver of a second after the universe was born, everything was unthinkably hot and crushed together. And in that furnace, physicists suspect, these separate forces were merged into a single, unified force. One force to run everything. As the universe cooled and spread out, that one force split apart into the different forces we see today, the way a single beam of white light splits into separate colors through a prism. This idea carries a grand name. Scientists call it grand unification, the dream that all the forces were once one. It is one of the most beautiful ideas in all of physics, and enormous amounts of work have gone into chasing it. Here is the catch, and it is a big one. If the forces really were once one, then deep down they must still be secretly connected, and that hidden connection comes with a price. The math says it should be possible, on incredibly rare occasions, for the pieces inside a proton to transform into something else entirely. Remember, a proton is built from quarks. In our everyday world, quarks stay quarks, locked in their roles, and the proton holds together. But if grand unification is true, then once in a great while a quark could morph into a different kind of particle, and the instant that happens, the proton is doomed. It can no longer stay a proton. It breaks, flashing into lighter particles that scatter away, and the proton is simply gone. So the dream of unification drags a heavy shadow behind it. The very same idea that makes the universe elegant and connected also means the proton cannot live forever. If all the forces were truly one at the start, then the great survivor, the rock under all matter, must eventually crumble. This is why so many physicists take proton decay seriously. It is a firm prediction that falls straight out of some of the most respected ideas about how the universe is built. If those ideas are right, the proton has an expiration date, even if that date lies almost unimaginably far away. There is a way to test it, at least in theory. If quarks really can morph, then a proton should break in a very specific way, throwing out a particular set of lighter particles that scientists can describe ahead of time. So they know exactly what a dying proton should look like. They know the fingerprint to hunt for. All they had to do was build something that could watch enough protons patiently enough to finally catch one wearing that fingerprint. So they built a cathedral, a vast, silent chamber buried deep beneath a mountain, filled with the purest water on Earth and lined with thousands of golden eyes that never close. Deep beneath a mountain in Japan, there is a chamber that looks like something out of a dream. To reach it, you travel far down into an old mine, away from the noise of the surface into the quiet dark. There sits a gigantic tank. It stands taller than a 10-story building and holds 50,000 tons of water. Not ordinary water. This is the purest water on the planet, cleaned again and again until it is almost perfectly clear, so clear you could see much farther through it than through the cleanest air. Line the walls of this tank with thousands of large glass eyes, about 11,000 of them, round golden detectors, each one built to catch the faintest possible flash of light. They stare inward, into the water, from every direction, never blinking, never resting. The whole machine has a name, Super Kamiokande. Why water? Because water is packed with protons. Every drop is loaded with them, waiting inside the hydrogen that helps make water what it is. 50,000 tons of ultra-pure water is a mountain of protons, all gathered in one place, all being watched at once. If even a single one of them breaks, this machine is built to see it. Why go underground? Because the surface of the Earth is drowning in noise. Tiny particles rain down from space every second, crashing through everything, including your body right now. All that rain would swamp the detectors and bury the one signal they care about. So they placed the tank under 1/2 mile of solid rock, letting the mountain act as a giant shield, blocking the storm from above and leaving only silence. Now here is the payoff. If a proton inside that water ever does die, it will not go quietly. As it breaks apart, it flings out lighter particles moving so fast that they punch through the water, quicker than light travels through it. When that happens, they leave behind a faint, ghostly ring of blue light, a tiny cone spreading out through the tank. That ring is the whole point. That is the fingerprint of a dying proton. The 11,000 golden eyes are there to catch that one flicker of blue, to freeze the exact moment a proton dies, and to prove that the great survivor is mortal after all. So the machine watches, year after year after year. In total darkness, under a mountain, thousands of eyes stare into a lake of the purest water on Earth, waiting for a single silent flash that might come at any second, or might never come at all. Teams of scientists take shifts, checking the data, scanning for that telltale ring. They have been at it for decades. Every day the tank holds its breath. Every day the eyes keep watch. Every day they wait to see history happen. The first proton ever caught in the act of dying. Picture the patience that takes. Imagine setting up a camera pointed at an empty field, then watching that screen every hour of every day for 30 years, certain that something might appear, with no promise it ever will. That is the job. That is the hunt for proton decay. So after all these years of watching, all these golden eyes, all this pure water and endless patience, how many dying protons has Super Kamiokande actually caught? The answer is haunting. Not a single one. After decades of watching, Super Kamiokande has caught exactly 0 dying protons. And strangely, that silence is one of the most important results in all of physics. Think about what the empty result actually tells you. If protons died even a little bit often, this machine with its ocean of protons and its thousands of unblinking eyes would have seen it by now. It would have caught the blue flash again and again. Instead, after all these years, nothing. Not one clean, confirmed death. That silence sets a hard flaw under the life of the proton. Because so many protons have been watched for so long with no death seen, scientists can say something powerful. The average proton must live for an almost unimaginable stretch of time before it breaks, if it ever breaks at all. How long? Try to hold this in your head. The universe is about 14 billion years old, and that already feels endless. 14 billion years, and not one proton in that tank has been caught dying. From that, scientists work out that a proton must last, on average, longer than the age of the universe multiplied by nearly 1 trillion. Take all of cosmic history, everything that has ever happened, and stack it up that many times over. The proton outlasts all of it. That is a level of stability the human mind was never built to picture. A proton is more patient than every star that has ever burned. It is steadier than whole galaxies. If it dies at all, it takes so long that the entire history of the universe so far is barely the first tick of its clock. Now here comes a twist that makes this silence even more valuable. Remember, some theories predicted that protons should decay. The simplest, most basic version of the grand unification idea gave a specific guess for how long a proton should live. And that guess was short enough that Super Kamiokande should have spotted dying protons by now, plenty of them. It spotted none. So that simplest theory is wrong. The silence killed it. The proton refused to die on the schedule the theory demanded, and that alone was enough to cross the idea off the list. In science, even a result of nothing can be a discovery. The empty tank ruled out an entire idea about how the universe works. This is one of the strangest kinds of victory in all of science. The scientists set out to watch a proton die. They have never once succeeded, and yet, by failing so carefully, for so long, they have learned something real. They have learned that the proton is even tougher and longer lived than most people ever dared to guess, and they have thrown out theories that could not keep up. The hunt is far from over. Right now, scientists are building even bigger tanks, with even more water and even more eyes, machines that could watch many times more protons at once. If the proton does die, on some far-off schedule, these next giants might finally catch that first blue flash and change the story forever. Until then, the proton keeps its deepest secret. We still do not know for certain whether it lives forever or is slowly dying. We only know that it is one of the most stubborn survivors in all of creation. And that stubbornness, it turns out, is the quiet reason you are alive to wonder about it at all. The proton's refusal to die is the reason there is anything at all to look at. Play out what would happen if protons were fragile. Suppose they broke apart easily, dying in years or days or minutes. Every atom in the universe is built around protons at its center. So if protons crumbled quickly, the atoms would crumble right along with them. Matter itself would rot away like fruit left out in the sun. There would be no lasting rock, no steady ground, no solid anything. Stars could never form and hold together long enough to shine. Planets could never gather and cool into worlds. And life, which needs billions of years of patient, stable matter to even begin, would never get its chance. A universe with fragile protons would be a place of pure decay, falling apart faster than it could ever build. That is not the universe we live in. Our protons are almost perfectly stable. They hold their shape for longer than the age of the cosmos, over and over. Because of that stubbornness, atoms endure. Rock stays rock. Water stays water. Stars burn steadily for billions of years, and enough time passes, calm and unbroken, for tiny chemical sparks to grow into living things, and eventually into you. So the next time you touch something solid, A wall, a table, your own arm. Remember what is really holding it together. Underneath it all sits a countless army of protons, each one refusing to fall apart, each one guarding its tiny piece of matter with a patience that outlasts the stars. Their stubbornness is the reason the solid world stays solid. There are more protons in a single glass of water than there are stars in the entire visible universe, and every last one of them is standing guard. This gives the whole proton decay question a weight far beyond a science experiment. When scientists watch that tank of water, waiting for a single flash, they are really asking about the fate of everything. If the proton is truly immortal, then matter has a kind of permanence, a promise that the building blocks will always be there. If the proton can die, even after unthinkable ages, then the universe has a slow expiration date built into its very foundation. Picture the far, far future. If protons do decay, then trillions upon trillions of years from now, long after the last star has burned out and gone dark, the protons themselves would begin to fade. One by one, across the cold and empty universe, they would break apart and vanish. The atoms would dissolve. Even the dead, frozen remains of stars and planets would slowly melt into nothing. The universe would drift into a quiet, total emptiness, as the last bricks of matter simply ceased to be. Whether that lonely ending is real depends entirely on the answer to a question we cannot yet solve. It all comes down to whether the proton, the tiny survivor inside every atom of you, is truly forever. For now, the proton stands firm, holding you and everything else together, guarding its secret close. But the proton has a next-door neighbour in the nucleus, a quiet cousin we met early in this journey, and that cousin does not share the proton's gift for survival. Set it free on its own, and it begins dying almost at once. Right beside every proton in the nucleus sits its quiet cousin, the neutron. And the neutron hides a dark secret. It is living on a timer. Remember the neutron from early on? It is built much like a proton from the same kinds of quarks, just arranged a little differently. It carries no electric charge, which is part of why it stays so quiet. And inside the nucleus, packed shoulder to shoulder with protons, the neutron is perfectly stable. Locked in that tight group, it can last as long as the proton does, sitting calm for billions of years. Pull a neutron out though, set it loose, all by itself, free from the nucleus. Now everything changes. A lone neutron does not stay a neutron for long. On its own, it dies. In about 15 minutes, a free neutron breaks apart and transforms into other particles. It becomes a proton plus a lightweight electron plus a tiny ghostly particle that streaks away almost unnoticed. The neutron is gone, and a proton stands in its place. Think about how wild that difference is. Inside the nucleus, a neutron can live for ages, steady and safe. Take that exact same neutron and set it free, and it survives only about 15 minutes. The neighbourhood alone is the difference between near immortality and a quick death. Company keeps the neutron alive. Loneliness kills it. 15 minutes may not sound dramatic, until you compare it to its cousin. The proton lasts longer than the age of the universe multiplied by nearly 1 trillion. The lonely neutron lasts about 1/4 of an hour. Two particles, almost twins, built from the same basic parts, and one of them outlives the stars while the other barely outlives a lunch break. Nature drew a razor-thin line between them, and no one fully understands why it falls exactly where it does. This dying act has a proper name. Scientists call it decay, the same word from the proton hunt, except here we can watch it happen easily, over and over. A free neutron breaking down is one of the most studied events in all of physics. It shapes how stars build new elements. It played a starring role in the first few minutes of the universe, when the very first atoms were forming out of the cooling fire of the beginning. So the neutron matters far beyond a science lab. The exact time it takes to die helped decide how much of each ingredient the young universe cooked up. Change that timer even a little, and the recipe of the early cosmos would come out different. Knowing the neutron's lifespan precisely is a key to understanding where the stuff of the universe came from. You would think, then, that scientists would have this number nailed down perfectly. It is one of the most important clocks in all of nature. Teams have chased it for decades, using the finest tools ever built, measuring it down to the last fraction of a second. Here is the problem. When they measure the neutron's lifespan 2 different ways, they get 2 different answers, not wildly different, just off by a handful of seconds, but those few seconds refuse to go away, no matter how carefully anyone checks. And a gap that small, in a measurement this precise, is exactly the kind of crack that can bring a whole new mystery spilling out. There are two main ways to time a dying neutron, and they stubbornly disagree. The first way is called the bottle. Scientists take a batch of slow, cold neutrons and trap them inside a special container, a kind of bottle they cannot easily escape from. Then they simply wait. After some time, they count how many neutrons are still there. Since free neutrons die, fewer of them remain as time passes. By watching how fast the neutrons vanish from the bottle, scientists work out how long a neutron lives on average. The bottle asks one simple question: how many are left? The second way is called the beam. Instead of trapping neutrons, scientists send a steady stream of them flowing through a detector, like a river of neutrons. As those neutrons fly along, some of them die in flight. And remember what a dying neutron makes. It turns into a proton. So the scientists count the fresh protons appearing in the beam. Each new proton marks one neutron that just died. The beam asks a different question: how many are being born? Both methods are brilliant. Both have been polished for years by careful, skilled teams, and both should give the exact same answer, because they are measuring the same thing, the lifespan of a neutron. Count the survivors or count the newborns, either way the neutron's clock should read the same. It does not. The bottle method says a neutron lives about 878 seconds. The beam method says it lives about 888 seconds. The gap between them is only around 9 seconds. In everyday life, 9 seconds is nothing about the time it takes to tie your shoe. But these measurements are so sharp, so carefully done, that a 9-second gap is enormous, far too big to be a simple mistake. For years, scientists assumed one team had made an error somewhere, a tiny flaw in the bottle, a hidden problem in the beam, so they checked and rechecked. They rebuilt their experiments, hunted down every possible source of error, and honed their tools to a razor's edge. The gap did not close. If anything, as the measurements got sharper, the two answers stayed locked apart, each side confident, each side precise, and still 9 seconds away from agreement. This became known as the neutron lifetime puzzle. Two of the most careful measurements in all of physics, aimed at the same simple number, refusing to match. It is the kind of thing that keeps scientists up at night, because it means one of two things must be true. Either there is a mistake so cunning that the best minds in the field cannot find it after decades of looking, or the neutrons are trying to tell us something new. That second option is the thrilling one. Notice how the two methods differ. The bottle counts how many neutrons are left. The beam counts how many protons appear. What if those two numbers fail to match because some neutrons are dying without turning into protons at all? What if a few of them are slipping away into something else, something the beam can never see? If that were true, the bottle would always come up a little short, exactly as it does. The missing seconds would be neutrons vanishing down a hidden path, and that hidden path might lead somewhere no one has ever been. What if some neutrons are escaping into a hidden world? That question sounds like science fiction, yet serious scientists have put it forward to explain the missing seconds. If a few neutrons in the bottle die without leaving behind a normal proton, then they must be turning into something invisible, something our detectors cannot catch. And that opens a door to some of the wildest ideas in modern physics. One idea points to dark matter. You may have heard the name. Most of the matter in the universe is not the ordinary stuff you're made of. It is a mysterious, invisible substance that gives off no light and barely touches normal matter at all. We know it is out there because we can feel its gravity tugging on stars and whole galaxies. Yet no one has ever caught a piece of it directly. It is one of the greatest unsolved puzzles in all of space. Now set the two mysteries side by side. On one hand, some neutrons seem to vanish without becoming protons. On the other hand, the universe is packed with invisible matter we cannot explain. What if they are connected? What if, once in a while, a dying neutron skips becoming a proton, and instead turns into a particle of dark matter, slipping silently out of our world and into the shadows? If that were true, it would be one of the biggest discoveries in history. It would mean the answer to the dark matter riddle had been hiding inside the neutron all along, showing itself as a tiny gap in a clock. A missing handful of seconds could crack open the darkest secret in the universe. There is an even stranger idea. and it is almost too bold to say out loud. Some scientists have wondered whether there might be a mirror world, a whole hidden copy of reality, with its own mirror particles and its own mirror atoms laid invisibly over our own. In this picture, a neutron could sometimes flip across into its mirror twin, vanishing from our side entirely, crossing into a reflection of our universe that we can never see or touch. It sounds like a fever dream. Yet it is written down in real papers, by real physicists, as a serious attempt to explain those missing seconds. That is how strange this small gap in a clock has become. To close it, people are reaching for dark matter and hidden worlds. Before you get swept away, there is an honest catch. So far, when scientists have gone looking for these vanishing neutrons directly, they have come up empty. Careful searches for neutrons slipping into dark matter have turned up no clear sign of it yet. The exciting explanations remain possible and unproven. The puzzle is still wide open, and the plainer answer, some subtle error no one has caught, is still very much on the table. That is the honest state of things. Two clocks disagree by 9 seconds. The reason might be a boring mistake, or it might be a doorway to dark matter, or even to a mirror universe. Right now, nobody knows for certain, and that not knowing is exactly what makes it thrilling. Both of these deep puzzles, the dying proton and the vanishing neutron, share the same root. They both spring from a force we can barely calculate, ruled by a theory so difficult that even the sharpest minds cannot fully solve it with pen and paper. We have a theory that describes the force inside the proton. The trouble is, almost nobody can solve it. The theory carries a heavy name, quantum chromodynamics. Under that mouthful sits a simple job. It is the rulebook for the strong force, the set of laws that decide how quarks and gluons push, pull, and cling together inside the proton. As far as anyone can tell, this rulebook is correct. Every time scientists find a way to test it, it passes. It is one of the great triumphs of human thought, so the proton should be an open book, right? We have the rules, we just plug in the quarks and the gluons, turn the mathematical crank, and out comes every answer we could ever want. The weight, the spin, the pressure, all of it solved, if only. Here is the cruel twist. Having the rules and being able to use them are two very different things. The equations of the strong force are so tangled, so ferociously complicated, that at the scale of a real proton, no human being can solve them with a pencil and paper. Not the smartest physicist alive. Not a whole room of them working for a lifetime. The math simply ties itself into knots too fierce to undo by hand. Why is it so hard? Blame that backward force again. Remember, the strong force grows stronger the farther apart things get, and it fills the proton with a blizzard of gluons that constantly spawn even more gluons and more quarks. Everything affects everything else, all at once, in a storm of endless feedback. In easier parts of physics, you can ignore the tiny effects and focus on the big ones. Inside the proton, there are no tiny effects to ignore. Every piece shouts at the same volume. The whole thing has to be solved together, or not at all. To feel the difference, think about predicting the path of a single thrown ball. That is a math problem a student can do. Now think about predicting the exact motion of every drop of water in a crashing ocean wave, all of them slamming into each other at once. That leap from one clean ball to a churning sea is close to the leap from easy physics to the inside of a proton. This is no small embarrassment. It is one of the deepest open problems in all of science. In fact, a piece of this exact puzzle is so important and so unsolved that there is a prize of $1 million waiting for anyone who can crack it with a proper mathematical proof. The money has sat there for years untouched. The greatest mathematicians on Earth have looked at it and walked away, so we are left in a strange spot. We hold what may be the correct rulebook for the heart of all matter, and we cannot read most of it. The proton obeys these laws perfectly, effortlessly, trillions of times over inside your body right now. Yet we, with all our cleverness, cannot follow the same math the proton solves without even trying. For a long time, that wall seemed to block the way forward. If you cannot solve the equations by hand, how do you ever pull real answers about the proton out of them? The way through did not come from a smarter person. It came from a machine. Scientists decided that if they could not solve the proton themselves, they would build one piece by piece inside a computer. If you cannot solve the proton with a pencil, You build one inside a computer instead. That is exactly what scientists decided to do. Since the equations of the strong force are too tangled to solve by hand, they handed the job to some of the most powerful machines ever made. The plan is bold. Rather than calculate the proton with clean math, they recreate it piece by piece as a working model inside a supercomputer. Here is the clever part. In the real world, space is smooth and endless, and that smoothness is part of what makes the math impossible. So scientists cheat. They chop space and time into a tiny grid, like turning a smooth photo into a checkerboard of squares. Instead of tracking the proton across endless smooth space, they only track it at the crossing points of the grid. It is like building a curved shape out of tiny square blocks. The result is a little rough, but with enough small blocks it gets close. On that grid, they place the quarks and the gluons, and they load in the rules of the strong force at every single point. Then they turn the computer loose. At each crossing of the grid, the machine calculates how the quarks and gluons pull and push, then it does it again for the next point and the next, folding all those pieces together into one giant grinding calculation. This whole method has a name. Scientists call it lattice work. After the grid, the lattice that makes it possible. The amount of number crunching is staggering. To model even a single proton this way takes a machine doing trillions upon trillions of calculations, running for a long time, burning through more computing power than almost any other problem in science. These are not laptops. They are room-sized supercomputers, some of the fastest that humans have ever built, sweating for weeks to capture one tiny particle, and it works. When scientists build a proton on the grid and finally add up all the churning energy of its quarks and gluons, the weight the computer spits out matches the weight of a real proton measured in the lab. The two numbers line up. That match is a quiet triumph. It means the rulebook really is correct, and that we can now pull real answers out of it, even without solving it by hand. This is how many of the proton secrets are being cracked today. The share of the spin carried by the quarks, the way the pressure spreads from the center outward, the exact recipe of the missing weight. Piece by piece, the grid inside the computer is filling in the picture that pure math cannot reach. Step back and see how strange this is. To understand the smallest, most common particle in matter, we have to summon the largest, most powerful thinking machines we own, and even then it takes them weeks of grinding. A proton solves its own physics instantly, endlessly, without effort, trillions of times over inside a single drop of your blood. We need a supercomputer just to copy a shadow of what it does for free. The proton, it seems, is the ultimate teacher. It humbles our best math and our best machines at the same time. And nowhere is that lesson clearer than in the place protons do their most important work of all. A place where they burn ever so slowly to give us light and life. The heart of the sun. At the center of the sun, protons are burning to keep you alive, and they burn in the slowest, most reluctant fire in the entire universe. Here is what powers the sun. Deep in its core, the pressure and heat are beyond imagination. The temperature there is around 27 million degrees Fahrenheit. Protons are crammed together so tightly and moving so fast that, once in a while, two of them slam into each other and stick, fusing into something new. That fusing releases a burst of energy. Trillions upon trillions of these tiny bursts happening every second add up to all the light and warmth the sun has ever given off. Every sunrise you have ever seen is protons fusing in that furnace. Every second the sun turns about 4 million tons of itself into pure light, and every bit of it begins with protons fusing. You would think, with that much heat and that many protons packed together, fusion would happen easily, constantly, in a roaring blaze. It does not. The first step in the process, two protons joining together, is one of the hardest, rarest events in all of nature. Why? Two things fight against it. First, both protons carry a positive charge, and like charges shove each other away, hard. Getting two protons close enough to fuse is like trying to press together the wrong ends of two strong magnets. They resist with everything they have. Only the wild speed and crushing pressure of the sun's core can force them near each other at all. Second, even when two protons do touch, they almost always bounce right back apart. To truly fuse and stay joined, one of the protons has to change, at the exact instant of contact, into a different kind of particle. That change is controlled by the weak force, the same shy force behind the dying neutron. And the weak force is so slow and so reluctant that this change almost never happens in time. Nearly every collision fails. So how rare is it? Here is the number that stuns people. In the core of the Sun, an average proton has to wait around 1 billion years before it finally fuses with another one. 1 billion years. That single proton is bouncing off other protons constantly, countless times every second, for 1 billion years, before it manages to stick even once. The fire of the Sun at the level of a single proton is the most patient, reluctant flame imaginable, where each proton waits an age for its one moment. Picture a giant lottery where you buy a fresh ticket every single second, all day and all night, and never stop. And even then you have to wait around 1 billion years on average before you finally win just once. The protons in the Sun's core are stuck in that exact lottery, colliding endlessly, almost always losing. The Sun shines because every second a few of them beat those impossible odds. It seems almost broken. The Sun is enormous, blazing, and ancient, and its fuel burns with a fire so slow that a single proton waits 1 billion years for its turn. You might expect that to make the Sun weak or dim. Instead, that very slowness is the greatest gift the proton ever gave us. Because a fire this reluctant does something wonderful. It lasts. The Sun's slow fire is the reason you're here to feel it. Think about what would happen if proton fusion were easy. If protons fused the instant they met, the Sun would not burn gently for ages. It would set off all its fuel in a wild rush and tear through it in the blink of a cosmic eye. A star like that would flare up brilliantly and then die, burning out in a tiny fraction of the time our Sun has lasted. There would be no long, steady warmth, just a quick flash and then darkness. Because proton fusion is so reluctant, the opposite happens. The Sun sips its fuel instead of gulping it. Each proton waits its long turn, and the Sun releases its energy slowly, evenly, and patiently. That patience is why the Sun has been shining steadily for billions of years already, and why it will keep shining for billions more before it finally fades. That long, steady burn is everything. Life did not appear overnight. It took an almost unthinkable stretch of time for simple sparks of chemistry on the young Earth to grow, step by slow step, into plants and animals, and finally into people. That journey needed a warm, stable star hanging steady in the sky for billions of years, never flaring up, never burning out too soon. A calm, reliable Sun was the one thing life could not do without. The reluctant proton gave us that Sun. The same shyness of the weak force that makes fusion so rare is exactly what stretches the Sun's life across billions of years. The very thing that looks like a flaw, a fire almost too slow to work, turned out to be the reason there was enough time for life to begin at all. If protons fused easily, the sky would be full of stars that lived fast and died young, and there would be no one around to look up at them. So the next time you feel sunlight on your skin, remember the strange chain behind it. That warmth travelled from the core of the Sun, where a proton finally fused after waiting 1 billion years, releasing a spark of energy that climbed slowly to the surface and then raced across space to reach your face. The gentleness of that fire, the patience of those protons, is woven into every sunny day you have ever had. It is humbling to realise how much hangs on such a tiny, stubborn particle. The proton holds atoms together, so that matter can exist. It refuses to die, so that matter can last. And it fuses so reluctantly that its fire burns slow enough for life to take root. At every level, from the smallest atom to the largest star, the proton has quietly made your existence possible. We have travelled a long way inside this one tiny particle. We have seen its weight born from pure energy, its spin gone missing, its pressure crushing a neutron star, and its life stretching past the age of the universe. We have watched it power the Sun and guard the future of all matter. And here is the humbling truth at the end of it all. For everything we have learned, the proton is still keeping secrets. The deepest questions about it remain unanswered, waiting for the next generation to solve, which is why, right now, scientists are building a brand new machine, one designed to finally see inside the proton more clearly than ever before. To finally see inside the proton scientists are building a machine unlike any before it. It is called the Electron-Ion Collider, and it is rising right now at a laboratory in the United States. It will be the first machine of its kind anywhere in the world. Its job is simple to say and staggering to do. It will take clear, sharp, three-dimensional snapshots of the inside of a proton, mapping the churning quarks and the blizzard of gluons in more detail than anyone has ever managed. The idea works a little like a hospital scanner. When a doctor wants to see inside your body without cutting you open, a special machine builds up a full picture from many cross-section images. The new collider aims to do the same for the proton. It will fire beams of electrons into protons over and over, from many angles, and use the way they scatter to slowly build a map of the secret world inside. Scientists are hungry for what it might reveal. Remember all the mysteries we have gathered on this journey, the missing spin still not fully counted, the blizzard of gluons glimpsed only in blurry snapshots, the exact way weight and pressure spread through that tiny space. The new machine is built to chase all of it, to turn our fuzzy, smeared pictures of the proton into something sharp and clear at last. If it works as hoped, it could finally close some of the oldest open questions about the proton. It might pin down where the spin truly comes from. It might reveal how the gluons arrange themselves inside. It might show us, for the very first time, a real map of the storm at the centre of all matter. A whole generation of discoveries could pour out of it. But even the greatest machine will not answer everything. Some of the proton's riddles are likely to survive it, waiting for machines and minds not yet born. Does the proton ever truly die? Which clock for the neutron is right, and does a hidden world lie behind the gap? Can anyone ever fully solve the tangled math of the strong force? These questions may outlast all of us. And maybe that is the most wonderful part of this whole story. The proton is the oldest, most common building block in the solid universe. It sits inside every breath you take, every drop of water you drink, every beat of your heart. It has been resting quietly inside atoms since a few seconds after time began. It could hardly be more ordinary or more close to you. And yet, after 100 years of the finest minds and the greatest machines humanity can build, we still cannot fully explain it. We cannot cleanly account for its spin. We cannot agree on the fate of its cousin. We cannot even solve the rules it follows without begging a supercomputer for help. The most common thing in your body remains one of the deepest mysteries in all of science. So the next time you look at your own hand, remember what it truly is. A vast collection of tiny, ancient, screaming furnaces, each one holding a pressure greater than a neutron star, each one a survivor older than the Earth, each one still guarding secrets we have chased for a century and never fully caught. You're made of mysteries, and we have only just begun to understand them.